Hi guys, welcome to Gatematic. In the previous lecture, we have completed the losses in transformer and we solved some previous year gate problem related to losses in transformer. Now in this lecture, we will start efficiency of transformer. So let's get started. Before starting efficiency of transformer, I would like to tell to a student that I have created the two module. First module is the NPTEL. This module 1 is the NPTEL lecture given by Professor D. Kastha sir. This NPTEL lecture is totally theoretical lecture. You can study transformer in detail in mode 1, and I have created a mode 2, that is module 2. Mode 2 is some important concept plus problem solving. So those who are in second year and they have not studied the transformer in their BTech curriculum, they should watch first module 1, that is the NPTEL lecture, then proceed to module 2. And those who have already studied transformer one time, they can directly switch to module 2, no problem. Okay, now let's start efficiency of transformer. In the previous lecture, we have gone through the losses in transformer. So it is very important to understand at what efficiency the transformer is working. In order to understand the concept of efficiency, let us try to understand what is fraction of load first. What do you mean by the fraction of load? You must understand this. In the previous lecture, I told you this fraction of load is denoted as X. So what do you mean by this? Let us try to analyze this fraction of load practically. Suppose we have one transformer, okay, and I am considering this as an ideal transformer. Now this transformer having rating 10 kVA. This is the rating of transformer, and let us say this is a step up transformer 100 by 200, having number of turns 100 is to 200, and I am considering this ideal transformer. Got it? Now I am connecting a load. This load is having 1 kVA rating at 0.8 power factor. This load is consuming 800 watt of active power. Got it? By going through power triangle, you can easily calculate the active power drawn by load, that is 800 watt. So in the question, the load is given like 800 watt 0.8 power factor, or they will give you in kVA also. Now I would like to ask you at what fraction of load this transformer is working. So fraction of load means rating of load connected upon rating of transformer. Okay, so it will be equal to load is connected 1 kVA and this is 10 kVA rating. So overall it will come out to be 0.1, means this transformer is working at 10% of load. This is very important to know at what fraction of load this transformer is working. In the numerical you will see that transformer is working at half load. So what do you mean by that? At half means the value of X is given, that is equal to half. Transformer is working at 33.3% of load. That means X is equal to 1 by 3. So these things you have to keep in mind. So the permissible value of X lie between 0 to 1 only, because we cannot connect a load of value 11 kVA. Why? Because the rating of transformer is 10 kVA only. So if I will connect the load having value more than 10 kVA, then this transformer will burn out. So the range of X will be either lie in between 0 to 1 only. Now one more point I would like to add, that is, we know apparent power is equal to V into I, that is product of voltage into current in transformer. Let us say this is V1 into I1. This V1 is the supply voltage. Okay, so this will be constant for any transformer, and I1 depend upon the load, or you can say, let us say apparent power, output power is V2 into I2. Now this V2 will be constant and I2 depends upon the load. So I can say kVA of transformer or load connected in transformer is directly proportional to the current. I can say this because when load will change, then current will change, and correspondingly power drawn from the transformer will change. Got it? So these things you should know, and some part I have already explained in the previous lecture, that is losses in transformer. Now move to the efficiency of transformer. Mathematically, efficiency is defined as ratio of output power upon input power. Let us consider one transformer, and I am not considering ideal transformer, this is practical transformer, and here load is connected, and this load having power factor that is equal to cos phi 2. Here I2 current is flowing, this is V2 and this is V1. So what will be the value of output power? Output power is given as in terms of watt, that is V2 I2 cos phi 2. I can write like the active power drawn by the load is V2 I2 cos phi 2. Now input power I can write output power plus loss. Okay, so output power is already, that is V2 I2 cos phi 2. Okay, and plus loss. In transformer we have already seen there are two types of loss. First one is a constant loss, that is known as iron loss, and second is the copper loss. So it will be equal to iron loss plus copper loss. Okay, so this is the formula of efficiency at any load. Here I am not saying this transformer is working at full load or this transformer is working at half load. Now let us say this transformer is working at full load, then the efficiency will be equal to V2, this I2 at full load only. The load current flowing at full load will be the rated current, right? So I can write I2 FL into cos phi 2 upon V2 I2 FL into cos phi 2 plus iron loss will not depend upon the load. Iron loss is the constant loss, it will not depend upon the load, so iron loss will remain at as it is, and this copper loss I will get at full load, that is PCU FL. Got it? So this is the formula of efficiency at full load. Transformer is working at full load means this is the kVA rating of transformer. V2 into I2 full load will give kVA rating of transformer. Okay, this is the kVA rating of transformer multiplied by power factor of load cos phi 2 upon kVA rating of transformer, that is the output power, plus Pi plus PCU at full load, means at full load current the copper loss I will get, that is PCU at full load. So this is the formula I am getting at full load. Now let us consider at any load. I am not talking about the full load, I am talking about at any load. Let us say at half load or 1/3 load or 2/3 load, the transformer is working at any load, we don't know. So in that case, what will be the current drawn by the transformer? The current drawn by the load from transformer I2 will be equal to X times of I2 full load. I can write like this, where X is the fraction of load. Suppose the transformer is working at half load and full load current is 50 ampere, means the current flowing at half load will be 1 by 2 multiplied by 50, that is equal to 25 ampere. In this way I can write, since I2 will be equal to X times of full load current, so we can say in that case the copper loss, we know the copper loss is directly proportional to the current square of current. So copper loss will become X square times of full load copper loss. I can write this like this, I2 and copper loss. Now I can easily calculate the formula of efficiency at any load, that is equal to V2 I2 cos phi 2 upon V2 I2 cos phi 2 plus Pi plus PCU. This is the generalized formula of efficiency. Now at any load, replace I2 is equal to X times of I2 full load and copper loss is equal to X square times of full load copper loss. You will get X times of V2 I2 full load into cos phi 2 upon X times of V2 I2 full load into cos phi 2 plus Pi, and copper loss can be represented as X square times of full load copper loss. Okay, so this is the efficiency, the formula of efficiency at any load where X is the fraction of load that we have already discussed. What I did, I replace I2 with X times of I2 full load. Why I am replacing? Because it become easy to handle the numerical. How? Let us see. I can write X times of this V2 into I2 full load is nothing but the rating of transformer. Okay, so I can write like kVA rating of transformer into cos phi 2 upon X times of kVA rating of transformer into load power factor plus Pi plus X square times of PCU at full load. Now see why I manipulate the formula in terms of this. In any numerical you will see the rating of transformer is given, means the kVA rating is given. Also the power factor of load is given and the fraction of load is given. So I manipulate the formula in terms of fraction of load and kVA rating so that it will become easy to handle each and every numerical. I will solve some problem that has been asked in previous year GATE exam. Then you can easily understand why I am writing if the mathematical formula of efficiency in terms of kVA and X. Got it? So this formula you have to keep in mind. This is very important. Only you need to know at what percentage of load the transformer is working. Suppose the transformer is working at half load, put X is equal to 1 by 2. Rating of transformer is given, suppose 10 kVA, so 1 by 2 into 10 into cos phi 2 is given, and you can easily calculate. Now here this full load copper loss is also constant, means the copper loss we are getting at rated current, and we know rated current generally in transformer rated current is given or full load copper loss is given. So by using this formula our calculation will be easy. That's why I am not saying you to mug up this formula. I am saying you to mug up this formula that is represented in terms of fraction of load and kVA rating. Got it? So finally I got the efficiency formula this much. Now this formula is not in per unit. Suppose in any numerical per unit values of voltage, current, uh, or losses, copper loss or iron loss is given, then how to approach in that question, that we are going to see. This is the efficiency at any load. This formula you have to keep in mind. Now I would like to derive one more formula, that is efficiency in per unit. Suppose each and every term is given in per unit, then what you have to write? Per unit is nothing but the representation of any value with respect to its base value, right? Suppose here x into kVA into cos phi is given. This is the output power. So we can represent output power in terms of per unit, that is we divide by the rating of transformer, that will give me the per unit value. So divide numerator and denominator by the rating of transformer, you will get the per unit formula of efficiency. Okay, so divide by kVA, numerator and denominator both, you will get x times of cos phi 2. This kVA will get cancel out. In the denominator also it will be equal to x times of cos phi 2 plus pi upon kVA rating of transformer. This will give you the per unit iron loss. So I have to write iron loss in per unit, and this will be equal to x square times of full load copper loss in per unit. So you have to take each and every parameter in per unit value. That's all. Only the kVA rating will cancel out because we are taking kVA rating as a base value. So these two formula you must know before solving any kind of problem from efficiency of transformer. Now let us move forward. That is, let us understand one more thing, that is at what load we will get maximum efficiency. Generally the question is asked, at what fraction of load we get maximum efficiency. This fraction of load is nothing but at what x only. Okay, so at what x we get maximum efficiency, that we should also know. So in order to know at what fraction of load we get maximum efficiency, we have to differentiate with respect to x. Okay, so let us write the efficiency formula, that is x into kVA by cos phi 2 by x into kVA cos phi 2 plus pi plus x square PCU full load. So divide both by x, you will get kVA into cos phi 2. Okay, and take x common from numerator side. So it will be equal to kVA into cos phi 2 plus pi upon x plus x into PCU full load. The formula of efficiency will become like this. Now see, this rating of transformer is constant, load power factor is constant. So this value is constant and this value is constant. It is not depending upon the load. Only the variable parameter is this losses. Okay, so in order to find at what load we get maximum efficiency, what we will do, we differentiate this dn with respect to fraction of load and equate it to 0. Means finally what I will get, I will differentiate this much, d by dx of pi upon x plus x times of PCUFL. You can apply u by v method also, means v into derivative of u minus u into derivative of v, you will get this much only. Okay, so it will be equal to pi upon x square is equal to PCU full load. So finally the fraction of load x will come out to be under root of iron loss upon full load copper loss. Remember, this is the full load copper loss. means the copper loss we are getting at rated current, that is denoted as PCUFL. So this much fraction of load we will get maximum efficiency. This is the condition for getting maximum efficiency. Okay, so whenever the question is framed at what fraction of load we will get maximum efficiency or find the maximum efficiency, so in order to find the maximum efficiency, what I will do, first I will find x by putting under root pi by PCUFL by using this formula. Okay, and after finding x I will put x in this equation. This is the formula of efficiency. Okay, I will put x in this equation and I will get the maximum efficiency. Got it? So this much concept you should keep in mind while solving any kind of problem in efficiency of transformer. So let us try to solve some previous year gate problem based on the concept which we have studied in this lecture. Let us see the first problem. In a 50 kVA 11 kV by 400 volt transformer, the iron and copper loss are given 500 watt and 600 watt respectively under rated conditions. See, these two losses are given under rated condition, means what is given? Pi is given, that is equal to 500 watt, and PCU under rated condition is denoted as PCU full load. This is given, okay, 600 watt. Calculate the efficiency on unity power factor at full load. What is saying? We have to calculate the efficiency at full load, means the value of x is given, that is equal to 1. This is the fraction of load. So at full load the fraction of load is equal to 1, that is x is equal to 1, it is given. Also unity power factor is given, that is cos phi 2 is equal to 1. So first find the efficiency. We have already gone through the formula. This is the formula. Now you can understand why I denoted the formula of efficiency in terms of x and kVA, because see, this 50 kVA is given, so I can write 50 directly, and x is given full load, x is equal to 1, so I can write cos phi 2 is equal to 1 is given, so I can write. Now you will say I will not use this formula, I will use V2I2 cos phi 2 by V2I2 cos phi 2 plus Pi plus PCU. Okay, no problem, you can go through that, but before that you have to find the value of I2, that is the full load current. So you can easily find the value of I2 full load current from here, but why to increase the number of steps? In gate exam you should reduce the steps so that you can get the answer quickly. So apply this formula, this will give you the quick result. So apply this, x is 1, so put 1, this will be equal to 50 kVA, so I am writing 50,000 multiplied by cos phi is 1 by 50,000 into 1 plus iron loss is given, that is 500 watt, and copper loss is given 600 watt. Okay, the value of x is 1, and this copper loss is the full load copper loss, remember this point. So you will get the efficiency equal to 97.84 multiplied by 100, you will get efficiency in percentage, it will be equal to 97.84. now tell me, is this a maximum efficiency? No, this is not the maximum efficiency. This we have calculated the efficiency at full load, and it is not necessary that at full load you will get a maximum efficiency, it depends upon the fraction of load. Okay, now see the second problem. Find the load for maximum efficiency and the iron and copper loss corresponding to this load. Now I have to find the load for maximum efficiency, means I have to find the fraction of load at which we will get a maximum efficiency. So in second case, find the load for maximum efficiency. First we have to find the fraction of load. I told you fraction of load at which we get maximum efficiency is equal to x, and that is given as under root of Pi upon PCU full load, and the value of Pi is given, that is 500 watt, and PCU full load is given 600 watt. So it will come out to be 0.912. What do you mean by this? Means at 91.2% of load we will get maximum efficiency. So at this x, kVA rating of load will be equal to x times of transformer kVA rating. Okay, so this will be equal to 0.912 multiplied by 50 kVA, 45.6 kVA. What do you mean by this? This means if I will connect 45.6 kVA of load, then I will get the maximum efficiency, means the transformer will work at maximum efficiency. Second thing, we have to find the iron loss at maximum efficiency. We know iron loss is the constant loss, so it will not depend upon the load, it depends upon the supply voltage and frequency, and in transformer supply voltage and frequency are constant. So Pi will not change. So Pi at this load will be equal to 500 watt only. Okay, but copper loss will change because we know copper loss is equal to x square times of PCUFL. We know this. So copper loss will depend upon the fraction of load. So by finding the copper loss, I will get this is equal to 0.912 chi square into 600. So this will be equal to 499.04. While finding maximum efficiency, we are getting iron loss is equal to copper loss. At this fraction of load, we are getting maximum efficiency, and at maximum efficiency, iron loss is I am getting 500 watt. That is the constant loss, and a copper loss also I am getting approximately 500 watt. So without using this formula, also I can easily write at maximum efficiency Pi is equal to PCU, that is equal to 500 watt. Iron loss is equal to copper loss, or you can say variable loss must be equal to the constant loss. So either you can apply PCU is equal to x square times of PCU full load, or you can directly write Pi is equal to PCU is equal to 500 watt at maximum efficiency. Okay, let us see the next problem. The efficiency of 100 kVA transformer is 0.98 at full, that is, this is the full load as well as half load. Means efficiency is equal to 0.98 at full load or at half load. It is same in both the cases. Means when x is equal to 1, then also x efficiency is 0.98, and when x is equal to 1 by 2, that is the half load, then also efficiency is 0.98. For this transformer at full load, the copper loss is less than the core loss, or is equal to core loss, is more than the core loss, or none of the above. Means we have to find the relation between copper loss and iron loss at full load. See, I can write efficiency is equal to 0.98 is equal to x times of kVA into, I can write the formula of efficiency like this, and efficiency is given, that is 0.98. Put the value of x at x is equal to 1. This will be equal to, kVA rating is already given, that is 100. Let us write in kVA only. Cos phi 2, power factor is not given, so take 1. Suppose in question power factor is not given, so take power factor is 1. So it will be equal to 100 by 100 plus Pi plus PCUFL, that is equal to 0.98. So by taking x is equal to 1, I am getting first equation. This is the first equation. Okay, and second equation, by taking x is equal to 1 by 2, so it will be 1 by 2 into 100, it will be 50 by 50 plus Pi plus x square times of PCU full load, so it will be equal to 1 by 4 times of PCU full load, and this is also equal to 0.98 only. Okay, so by solving these two equation, I can easily get Pi and PCU full load, and by seeing these two, I can easily say which option is correct. So let's find the relation between Pi and PCU full load. I can easily relate these two because here RHS are equal, 0.98 and 0.98. So I can write 100 by 100 plus Pi plus PCU full load must be equal to 50 by 50 plus Pi plus PCU full load by 4. So this will be equal to this much, 100 plus 2 Pi plus PCU full load by 2 must be equal to 100 plus Pi plus PCU full load. So this 100 will get cancelled out, this Pi. Finally I am getting Pi is equal to PCU full load by 2. So finally iron loss I am getting less than the full load copper loss, right? From here I can say Pi is less than full load copper loss, and we have to find the relation between Pi and PCU at full load only. So iron loss is less than the copper loss, or we can say copper loss is greater than the iron loss, that is core loss. So option C is correct. Got it? Take one more problem in terms of per unit. We have already seen the efficiency in per unit, so take one problem based on that formula. The percentage resistance and percentage reactance of 10 kVA 400 volt by 200 volt 3-phase transformer are 2% and 10%. Internal percentage resistance RPU is given, that is equal to 0.02, and XPU is given, that is equal to 0.1. If the constant loss in the machine are 1%, means iron loss is given, that is equal to 0.01. The maximum possible percentage efficiency of the transformer, means we have to find the maximum efficiency. N max will be equal to what? So before finding maximum efficiency, what you have to find? You have to find at what fraction of load we are getting maximum efficiency. That means we have to find the x. So we have already seen at maximum efficiency the value of x is nothing but pi upon PCU full load. We have seen this. Okay, pi we already know, that is 0.01 per unit, but we don't know the full load copper loss. But I have already explained you in one of the lecture, that is the lecture number 3, equivalent circuit and per unit, that is PCU full load in per unit is equal to the internal resistance in per unit. So it is given, that is 0.02. Keep in mind, I have already explained you how this formula is coming in the lecture number 3. Go through that. So finally I will get x is equal to under root of pi, that is equal to 0.01 by 0.02. So it will be equal to 1 by root 2. Now once we got the value of x at which we are getting maximum efficiency, then apply the formula. N max, that is equal to x times of kVA into cos phi 2 by x times of kVA into cos phi 2 plus pi plus x square times of PCUFL. So if I am writing N max, then pi is equal to PCUFL. Definitely I will get. Now put x is equal to 1 by root 2, means we have already found the value of x at which we are getting maximum efficiency. 1 by root 2 multiplied by kVA rating, that is given as 10 kVA. But here we are taking all the things, that is iron loss or copper loss in per unit, means we have to take kVA rating also in per unit. So this kVA rating in per unit will be 1 per unit, because 10 by 10 I will get 1 per unit only. So it will be 1, and here power factor is not given. So take power factor as 1. So it will be equal to 1 by root 2. Pi is given 0.01, and x square times of PCU full load, you will get 0.01 only, because at maximum efficiency iron loss and copper loss both are equal. Multiplied by 100, finally you will get the maximum efficiency, that is equal to 97.24. So option B is correct. In this way you can approach any kind of problem related to efficiency of transformer. Only you have to keep in mind the formula of efficiency that I have shown to you, that is equal to x into kVA cos phi 2 by x into kVA cos phi 2 plus pi plus x square PCU full load. This formula you have to keep in mind. If you know this much, then you can easily solve each and every problem related to efficiency of transformer. You can also go through V2I2 cos phi 2 by V2I2 cos phi 2 plus pi plus PCU. That is also correct. I manipulate that formula in terms of kVA, because generally in any kind of problem they will give you the kVA rating, so it becomes easy for you to find efficiency by using this formula. In the next lecture we will see some more previous year gate problem related to efficiency of transformer. Thanks for watching this video.